All righty. All right, Chemistry 3101. This is Chapter 2, Molecular Representations. We've already covered bond line structures in the first chapter, and we're going to get into those in more detail in this chapter. We're also going to talk more about partially condensed structures and look at formal charges a little bit more and things of that nature. So when we represent molecules, if you go back to your Gen Chem 1 days, really you would have looked at, honestly, you would have looked at molecular formulas more than anything probably in general chemistry, calculated molar masses. And the reason why you were so interested in molecular formulas in general chemistry is because you would have done a lot of stoichiometry calculations, right? Limiting reactants and all that kind of thing. But molecular formulas, the problem with molecular formulas in organic chemistry is it doesn't tell us anything about the structure of a molecule. Now, if you again go back to your general chemistry days, you would have talked about Lewis structures quite a bit, and we're going to use Lewis structures a whole bunch in this class. We'll use them every day. But the only thing about Lewis structures, their limitation is that they're really only good for small molecules. When you have a big molecule, it just becomes tedious to draw the Lewis structure. And so, you know, I've already introduced you to the concept of a partially condensed structure. And a partially condensed structure is simply one where we eliminate the carbon-hydrogen bonds. Okay, just get rid of those carbon-hydrogen bonds, and that eliminates a lot of bond drawing. So you can see that what they did here, going from the Lewis structure to the partially condensed structure, is if we have a methyl, CH3, right? They took those CH3 groups and they just condensed them to CH3 like this. And if you're wondering, you know, like, why is this one backwards? The reason why it's drawn H3C and the one on the right is drawn CH3 is because what they're trying to show you is that the carbon is attached to the carbon, right? If you wrote carbon, CH3, and then you write CH3 over here, it's okay, but it kind of looks like the carbon is attached to a hydrogen. So I like drawing it backwards the way they've done it here, okay? So we're getting rid of the carbon-hydrogen bonds. You can see here that we had a carbon-hydrogen bond, and they've gotten, actually, they didn't condense that one. They could have, but anyhow, they chose not to. But they did condense this one. This oxygen-hydrogen bond has been condensed here. So that's what we call a partially condensed structure. And then I showed you also this morning that you can condense a structure even further beyond a partially condensed. And that's where we try to condense basically everything that we can. And any groups that we have, we cluster them together. So if you look at the partially condensed structure, you see that we have two CH3 or two methyl groups, and they've put them here in this bracket. And then they use a subscript 2 to denote that there are two methyl groups, and then we have the CH and then the OH. And then a molecular formula, again, the problem with the molecular formula, if I was to say, you know, give me the structure of this compound, which is isopropanol, that's the compound that's on here, and you wrote this, that would be wrong because, again, it doesn't relate the structure, right? It could also be, there are several isomers of C3H8O. Where's my black pen? It could also be this. So it could be CH3, CH2, CH2OH. And this is not the same. These are not the same thing. And so, again, this is why we generally try to shy away from molecular formulas in organic chemistry. Give me a thumbs up if you follow me on the rationale as to why we don't use molecular formulas a ton in organic chemistry. Yeah, why we have to show the structure. Great. Awesome. Well, let's move on from there. I'll put an X over this just in case anybody pauses the video or something. All right, so let's see if we can draw a Lewis structure for each of these compounds. And you can see that they've clustered some of the groups together. So we've got this first one. So in B, you know what I'm going to do? I'm going to start with this CH group here. I'll start with that, and we'll say, okay, well, we've got a CH group. And then off of that, we have two CH2, CH3. So we have two of these. So we're going to write CH2, CH2, and then CH3. I might have to move this. So we have CH2, CH3. So we've got those taken care of. Now we have two CH2s coming off of the carbon in red. So I'm going to draw those here in green. Hopefully you can see that in the video. So we have two CH2s like this. And then we have our OH group here. So we're going to put O, H. And don't forget that when oxygen has two bonds, it also has two lone pairs. So there's our Lewis structure for this compound. Again, you've got to be able to go back and forth between condensed structures and Lewis structures and bond line structures, all that good stuff. Well, let's try the next one. Where I'm going to start is with this carbon here, and it's got an oxygen and a hydrogen attached to it. So I'm going to put carbon, oxygen, hydrogen, like this. And then attached to that carbon in black, I've got three CH2, CH3 groups. And of course, these groups do have names. These are ethyl groups. And if you've never seen that before, don't worry about it. We're going to get into that later. But if you've heard of those things, yes, those are ethyl groups. So I have one ethyl group here. There we go. I have a second one here. Kind of running out of space. Like that. And then we put the last one down here. There you go. There we go. So give me a thumbs up if you follow me on that. Any questions about taking the condensed structure? And these are fully condensed structures. Now, if you're saying, well, you already went over bond line structures with us earlier this morning. Could you draw the bond line structure of these? Sure, we absolutely could. If we were to draw the bond line structure of this one, we have our our OH group. Then we have one CH2, CH3. We have another one like this, and then we have another one like this. So that would be the bond line structure of this compound. It's not the prettiest bond line structure in the world, but it gets the idea across. And then for the one on the top, the way I would do this one is, since you have 5 carbons in a row here, like this, I would go 1, 2, 3, 4, 5. And then I would put the OH group on that. And then if we go 1, 2, 3, then we have 1, 2, like that. So that would be the bond line structure of the compound on the top. Now, you might need to pause the video if you go back and take a look at it and try these again. Again, it wasn't part of this question, but since it's something that we covered this morning, that is how you would draw the bond line structures of both of these compounds. Again, the one on the bottom isn't the prettiest the way I've drawn it, but it will work for now. All right, so bond line structures, a little bit more information about bond line structures. Here's a compound I'm sure you've all heard of before. This is an antibiotic known as amoxicillin. If you have an ear infection or something, you might get a prescription for amoxicillin. Costs only pennies per dose. Very inexpensive antibiotic. And you can see this is a pretty big molecule. And here's the Lewis structure, which is beautiful, I guess. But it's really hard to see what's going on here. It's very difficult to hone in on different portions of the molecule. And what we're going to get into in a little bit are functional groups. And there are several functional groups, right? We have an alcohol here. And if you don't know what the functional groups, don't worry, we're going to cover them today. We have a primary amine here. We have an amide here. But the idea is that, and there are others in here as well that I'm not going to circle right now, but the idea is that it's very difficult to see these functional groups. Whereas if we look at a bond line structure, so here's the bond line structure on the bottom, you can see that our eye is drawn to this group, and it is drawn to this group, right? And it's drawn to this group that I had pointed out before. So we can see the functional groups much more rapidly in a bond line structure. So not only does it save us time in drawing, but it enables us to sort of hone in on the functional groups, so to speak. Now, if you're wondering what the heck is a functional group, again, it's something that we're going to cover in a little bit. But the functional groups are usually where it's a site of reactivity oftentimes. And so we are interested in reactions, of course. We haven't gotten into any yet, but that's where we're headed. And so if you can produce a structure that enables you to hone in on the area of the molecule where a reaction can occur, that would be a good thing. So that's another reason why we like bond line structures. So bond line structures, again, just to rehash, are the benchmark representations for organic compounds. It is critical to know, how to draw these structures for any compound without difficulty to succeed in any organic chemistry course. So notice it says you should be able to draw these without difficulty. That means you have to master the subject of bond line structures. It cannot be escaped, my friends. You have to master it because it's what I'm going to use all the time moving forward. It's what our textbook is going to use most of the time. All right. And so you can see with this amoxicillin, how much faster it is, again, to draw compared to a Lewis structure. So bond line structures are a good thing. All right, so just a little bit more information about bond line structures, because I didn't show you one yet that had any double bonds or triple bonds in it. But just to rehash a little bit of what we went over this morning, is every corner or endpoint represents a carbon. Remember that carbon always has 4 bonds when it's uncharged. So here we have hexane is the first compound. This compound here is called hexane. This one here is called 2-butene. Again, the names aren't important. We're not covering nomenclature yet. And this one is called 2-butyne. But anyhow, I digress. What's being shown here again is that in this compound we have 1, 2, 3, 4, 5, 6 carbons. But the same thing is true when we have this double bond in 2-butene. We have 1, 2, 3, 4 carbons. So my question is to you. Let's just look at carbon number 2, for example. How many hydrogens are attached to carbon number 2? They aren't drawn in, right? Because we don't include hydrogens in a bond line structure. But how many are implied? No, there's not 2. There's only 1, right? Because the carbon currently has, watch my green pen, 1, 2, 3 bonds. Carbon always has 4 bonds. And therefore, it's implied that there is 1 hydrogen attached to this carbon. And for the same reason, there's only 1 hydrogen attached to this carbon. What about the carbons 1 and 4? How many hydrogens do they have attached to them? Exactly. There's 3, right? Because they each have 1 bond. So it's implied that there's 1, 2, 3 hydrogens here, and 1, 2, 3 hydrogens here. Let's move on to the next one. If we have 2-butyne, okay, if I look at carbons number 2 and 3, so I'm going to pencil them in here in green. How many hydrogens are attached to carbon number 2? Exactly. There's none, right? Because it has 4 bonds attached to it already. How many carbons are attached to, or sorry, how many hydrogens are attached to carbons 1 and 4? Exactly. There's 3. 1, 2, 3, and 1, 2, 3. There you have it, my friends. All right. So we've covered a little bit more of bond line structures in that we are looking at structures that have single and double bonds. So if you have an sp2 hybridized carbon, it's going to have 1 hydrogen attached to it. And if you have an sp hybridized carbon, you have to show not only that it has a linear molecular geometry, but that it has no hydrogens attached to it. So again, keep that in mind. When you have an sp2 hybridized carbon, like this carbon, where's my blue pen? Maybe I should erase some of this stuff, okay? If I look at the sp2 hybridized carbons, okay, this is sp2 and this is sp2, you still draw it in the zigzag format, just like you would in the sp3 hybridized carbons. But when it's sp hybridized, and we have sp hybridization for this carbon here and this one here, in that case, you draw it as linear, right? So what we're seeing here is CH3, carbon, triple bond, carbon, CH3, okay? But you have to show the linear molecular geometry here, that it has a bond angle of 180 degrees. All right, there we go. So again, if you have a heteroatom, so something like an oxygen, nitrogen, sulfur, etc., you include those in the structures. So let's say we have this compound here. This is called 2-pentanone. If you look at any of the carbons in there, okay, if we just put this carbon here and we highlight this one in yellow, how many hydrogens are attached to this carbon that I have highlighted in yellow? How many hydrogens are attached to this one? 0, right? Because it already has 4 bonds, right? It's attached to 4 lines. Therefore, it's got 4 bonds. We don't include carbon-hydrogen bonds. Ergo, it's got no carbon-hydrogen bonds, okay? What about if I highlight this one in blue? How many hydrogens are attached to this one? 3, exactly. And then the one in green has 2. The one in red has 2. And if I pick a different color, let's try something freaky here. Let's try purple. There we go. The one in purple has 3 hydrogens as well. So there you go. Bond line structures. So let's move on from there. It says practice identifying the locations of carbons and hydrogens in a skeletal structure. So I'll tell you what, let's go right to the big leagues. And why don't we start with this compound here, okay? Could anybody tell me, this one that I have in the green box, how many carbons are in this compound? Yeah, there's 6 carbons, right? So we have 1, 2, 3, 4, 5, 6. Could anybody tell me how many hydrogens are in this compound? How many hydrogens would there be? Right, there's 14, aren't there? Right, so if I change the color of these carbons, so why don't I make all these ones black, and I'll make these 2 red. So the ones that are in black all have 3 hydrogens attached to them, right, because they all have 1 bond. And the ones in red, they have 3 bonds already, so they only have 1 hydrogen attached to them. So that means the formula would be C6H14. So there you go. We've identified all of the carbons and hydrogens in this compound. All right, let's try something a little way more interesting. Let's try this guy here. Could anybody tally up the total number of carbons in this? I'll do it myself. Does anybody have the number of carbons in this guy? Yeah, so there's 15 carbons in this molecule. All right, let's draw them all in purple. So we have 1, maybe that's black. Yeah, it's black. 1, 2, 3, 4. Right? Remember that at this point right here, you go from a single bond to a triple bond, right? So that is implied that there is a carbon here. Okay, so we have, maybe I'll use a different color. Let's use blue. Here we go. So let's start over. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 carbons in this compound. And if we want to fill in all the hydrogens, on this carbon, we're going to have 2 hydrogens. If I highlight this carbon in yellow, could anybody tell me how many hydrogens are on this carbon in yellow? None, because it has 4 bonds. What about this second carbon in yellow? How many hydrogens on this guy? 0 as well, yeah. What about this carbon? I'll highlight this one in green. How many hydrogens on this carbon in green? 1, absolutely, right? Because it's already got 3 bonds. So we'll put 1 in here. We'll put 3 here. Right, I'm just filling them all in. So we have to have 3 on this one. Right, we have none there, none there, none there, none there. We have none there. We have 2 here. And then we have 3 more here. And 3 more here. All right, there you go. Oh, I'm missing one. Boink. There we go. Now we've got all the hydrogens drawn in there. All right. And you can see that whenever you have a hydrogen attached to a heteroatom, like the sulfur here, you include that. So any hydrogens directly attached to a heteroatom, they're included in the bond line structure. All right. So what's the best way to master this? Starts with P, ends with practice. That's right, practice. You're going to have to practice this over and over to master it. But again, like it said in the previous slide, bond line structures are the benchmark. It's the benchmark method of communication of structures in organic chemistry. All right. So we've already gone over the whole idea of zigzag. So when you have a straight chain, you have to draw it as a zigzag. It doesn't matter if you zig or zag first. Doesn't matter. These 2 things are perfectly identical. So again, that only applies for sp2 and sp3 hybridized carbons. The next rule is if you have a double bond, you try to draw everything as far apart as possible, right? And the reason why you want all the bonds as far apart as possible, that's based off of VSEPR, valence shell electron pair repulsion theory, right? Electrons want to be as far apart from each other as possible. And so this is kind of funny looking, but if you have a double bond and 2 singles, you want them to be as far apart from each other as possible. The next rule is when you have single bonds, the direction is really irrelevant. I try to spread them out as much as possible, but these 2 structures down here, they're identical to each other. Both of them are perfectly correct. Again, heteroatoms are always included. What's a heteroatom? Again, to repeat, It's nitrogen, oxygen, sulfur, fluorine, chlorine, bromine, iodine, though phosphorus would even fall in there, okay? These are the heteroatoms that we're going to see over and over. You always draw those in, and any hydrogens that are directly attached to them, you include those. So since we have an oxygen attached to this hydrogen, you include that hydrogen over here. And the cardinal rule, never draw more than 4 bonds to a carbon. Carbon is in the second period. It cannot exceed an octet of electrons. It's impossible. And so never, ever do that. In fact, if I ever see anybody draw a carbon like this, okay, we call this the Texas carbon, okay? And that is not a good thing, okay? So sorry if you're from Texas. It's not meant to offend or anything. It's just something that I learned down here in the States. They call that the Texas carbon. It's a big no-no, okay? Never draw a carbon with 5 bonds. I will never do that again, okay? That was a one-time thing. Let's go to the next slide. I feel weird. Okay, so now we're going to get into functional groups. And what are functional groups? It says it's a characteristic group of atoms or bonds that possess a predictable chemical behavior. Oh, this is getting more and more interesting all the time, because what do we want to do as organic chemists? One of the things we want to be able to do is look at a molecule and say, this molecule is going to react in such and such a way. This molecule is going to be oxidized. This molecule is going to be reduced. This molecule can react with an alcohol. This molecule can react with an amine. This molecule will make a salt. You know, these kinds of things. And if you're wondering, you know, predicting chemical behavior, could that also be related to how it would react inside the human body? Absolutely. Absolutely. And so this is why people who are interested in medicine have to understand functional groups, is because they have to be able to have some kind of prediction of what a molecule could do inside the human body. So it says here, memorize the functional groups on page 56. Well, this is an artifact of the olden days when we used the hard copy of the textbook. But I have a table here which covers, I think, the vast majority of the functional groups that you need to know. So this is table 2.1 from our textbook. Now, it's 8:51 in the morning, and what I'm going to do right now is I'm going to go into our class announcements quickly. And I don't want to inundate you with information, but I'm publishing an announcement right now where I have a link to a video on my YouTube channel where I cover all of the functional groups in detail. And the reason why I made the video is just so you can watch it and learn the functional groups. But I've taught this class long enough to know that, you know, there's only so much yammering on I can do about the functional groups. It's you that it's going to have to sit down and memorize each one of the functional groups. So I'm going to go through each one of them with you right now. And there's even one, I think, that you need to know that's not in the list on these 2 slides. And so again, to repeat, what the heck is a functional group? The functional group, if we go back, what's the whole point? It's because we can predict chemical behavior by identifying functional groups in a compound. So if we go back, all the way back to that structure of amoxicillin that we had, here it is, right here. Amoxicillin is called a beta-lactam, and that's neither here nor there. But there's functional groups. There's one here. There's another one here. This would be a functional group. This is a functional group. This is a functional group. And this is a functional group. And this could be considered a functional group. It's debatable, I guess. But anyhow, you can see that amoxicillin is replete with functional groups. And so a good medicinal chemist or a good doctor is going to be able to look at that molecule and make some prediction about the reactivity based on its functional group. So you've got to be able to identify those. And so let's go to the table and let's go through each one of them that you need to know. Is this an exhaustive list of all the functional groups in organic chemistry? No, not at all. But these are the first ones that you need to know. So the first one is an alkyne. And an alkyne, we've seen a couple this morning. It's when we have a triple bond between 2 carbons. So if you have a triple bond between 2 carbons, like this in the bond line structure, we call that an alkyne. And if you remember when we discussed pi bonds and sigma bonds, pi bonds are weaker than sigma bonds, and an alkyne has 2 pi bonds, and therefore that's where the reactivity of an alkyne comes from, because you have 2 bonds that are weak and so they can break. Anyhow, that's neither here nor there at the moment, but the next thing I want to address with you is, what is this R? Okay, why is there an R? What is that? Okay, if you're looking at your periodic table and scanning it, trying to find element R and you can't find it, well, there's a good reason, because there's no such thing as element R. What is the R group? Let me scroll down here and I'll show you. It says R refers to remainder of the compound. So it's usually just carbon and hydrogen atoms. So remainder is, so the R group is just a way to say, well, there's something attached to this. It's probably made out of only carbon and hydrogen. It's irrelevant because if we only have carbon and hydrogen and all the carbons are sp3 hybridized, we don't have any functional groups there. And so we just use R as a placeholder, so to speak. So there we go. There's an alkyne when we have a carbon-carbon triple bond. Another functional group that we saw a few times today was an alcohol, and that's when we have an R group attached to an oxygen and a hydrogen. And we talked about hydrogen bonding. And so if you're thinking, hey, wait a second, does that mean that this thing here, this OH group, if I have an alcohol, it can always participate in hydrogen bonding? The answer would be absolutely. Absolutely. Alcohols can always participate in hydrogen bonding. The next one is an ether. And an ether, it's kind of like an alcohol in a way, but you replace the hydrogen with an R group. So an alcohol looks like this. We have a hydrogen, whereas an ether, we replace the hydrogen, we replace this hydrogen with an R group instead, okay? So can an ether, if you just have a pure ether, can it do hydrogen bonding? Just yes or no? Could anybody say, if I have, two molecules of this, are they going to participate in hydrogen bonding? No. Even though there's hydrogen and oxygen in the molecule, the oxygen is not bound to a hydrogen, and therefore there's no hydrogen bonding. Good. All right, awesome. The next one is a thiol. If you're really into things that smell terrible, a thiol might be in your future, okay? So if you're looking at the alcohol and the thiol and you're saying, hey, wait a second, those are pretty similar. The only difference is I replaced the oxygen for a sulfur. You'd be absolutely correct, okay? So a thiol is basically the sulfur analog of an alcohol, okay? We just have an SH group. It doesn't participate in hydrogen bonding though, does it? Because sulfur is not fluorine, oxygen, or nitrogen. All right, so that's a thiol. And then if you're looking at these two, the ether and the sulfide, and saying, hey, wait a second, these look kind of similar too. All you did was replace the oxygen with a sulfur, and you go from an ether to a sulfide, and you'd be absolutely correct in that as well. Okay, sulfide. So with sulfide is when we have a sulfur with two R groups, but when one of the R groups is a hydrogen, then we call it a thiol. All right, the next one is an aromatic. So an aromatic compound is when we have 6 carbons in a ring, and then we have double and single bonds alternating. So if I draw the Lewis structure, or at least the partial Lewis structure, it's going to look like this. Forgive me, this is not my best artwork, but anyhow, it's going to have to do for today. There you go. You have 6 carbons in a ring, and you see how it goes double, single, double, single, double, single, right, for our bonds, okay? So we call that an aromatic ring, and you've probably noticed a few aromatic rings already. You saw one there was one in amoxicillin that we looked at. And you see that we're going to get, if you look at what chapter these are covered in, you see that in this class that you're currently enrolled in, you're going to cover alkyne chemistry in detail, but the chemistry of alcohols, ethers, thiols, sulfides, and aromatics, that's not covered until organic chemistry too. However, you still need to be able to identify the functional groups in this class. All right, moving right along. The next one is a carboxylic acid. And this is not to be confused with an alcohol, because you might look at this and say, well, look, I've got an oxygen and a hydrogen. Hey, that's an alcohol. No, it's not. When you're identifying functional groups, you have to take what I call the 30,000-foot view. You have to step back and evaluate the entire situation and say, well, wait a second. This oxygen is attached to a carbon with a double bond to oxygen on it. So when you take the whole group together, then you have a carboxylic acid. So where would you find a carboxylic acid in your everyday life? If anybody here has ever had vinegar before, like a balsamic vinegar, so acetic acid is a carboxylic acid that's found in vinegar. Propionic acid is what gives the tang in Swiss cheese. Anyhow, so carboxylic acid. The next one is an acyl halide. Sometimes I call these an acid halide. So again, when we're talking about X can be equal to fluorine, chlorine, bromine, and iodine, right? Because those are the 4 halogens, the halides. So if we have a carbon with a double bond to oxygen like this, and then we have a halogen attached to it, we call that an acyl halide or an acid halide. The next one is an anhydride. So if you look at this entire group here with these two R groups, we call that an acid, or we call it an anhydride. So we have a carbon with a double bond to oxygen, then we have another oxygen, then we have another carbon with another double bond to oxygen. Next one is an ester. We're going to talk about esters a little bit in this class. If you like the smell of things that are fruity, like strawberries, bananas, pineapples, cherries, even wintergreen gum, things like that, those are esters. So if you're thinking, man, I'd like to make some esters in the lab, instead of making something that smells awful, I could make something that smells great. Well, there is a lab that I do sometimes where we make, make esters that have great smells, great odors. But if you're looking at the ester and saying, hold on a second, it looks kind of similar to the carboxylic acid to me. Well, there are some similarities. The difference between the ester and the carboxylic acid is this, right? In the carboxylic acid, we have a hydrogen attached to the sp3 hybridized oxygen, whereas in an ester, we have an R group attached to the sp3 hybridized oxygen. All right, the next one is an amide. If you've studied biology and talked about peptides, has anybody here ever discussed peptides and proteins in biology class? So you might have heard of a peptide bond before. Well, a peptide bond is nothing more than an amide bond between two amino acids. Anyhow, so an amide is when we have a carbon with a double bond to oxygen, and then we have a nitrogen attached to it like this. So that is an amide. The next one is an amine, and we actually drew an amine earlier this morning. We drew trimethylamine. And an amine is where we have a nitrogen with R groups attached to it, so no carbon with a double bond to oxygen. Let's move on. If we have a carbon-carbon double bond, we call that an alkene. So carbon-carbon double bond, we have an alkene. And we drew a couple of alkenes this morning already. And the last, no, actually there's one more that I want to show you. So the next one is when you have a carbon with a double bond to oxygen. So you've noticed that there's a bunch of functional groups that have a carbon with a double bond to oxygen. If you don't believe me, check this out. A ketone has a carbon with a double bond to oxygen. An aldehyde has one. If you look over here, we see that a carboxylic acid has one, an acid halide has one, an anhydride has two, an ester has one, an amide has one. So you have all these functional groups that have a carbon with a double bond to oxygen, a whole bunch of them. So there's a name for that group. When you have a carbon with a double bond to oxygen like this, okay, we call that a carbonyl. Carbonyl. So instead of me saying C double bond O, that is incorrect. The correct term is a carbonyl. And so the way you would describe a ketone, you'd say I have a carbonyl attached to two R groups, and I have a ketone. Whereas when I have an aldehyde, I have a carbonyl and it's attached to one R group, but one of the R groups is a hydrogen atom. And that would give you an aldehyde. And formaldehyde would be an example of an aldehyde that you would know. All right, there's one more functional group that's not on here, and that is this one here. If you have an R group with NO2 attached to it, we call that a nitro group. All right, and instead of me drawing a compound that has a nitro in it, what I'm going to do is I'll draw the Lewis structure of a nitro for you, because it's got an interesting Lewis structure where you have a negative charge on one of the oxygens and a positive charge on the nitrogen. But if we have a positive and +1 and -1, they cancel each other out, which makes the nitro neutral. I think my students used to have some kind of, wake up drink or something called nitro. I don't remember. Anyhow, there we go. So those are all of the functional groups. Now, again, I've taught this class a long time. I know that there's only so much talking about functional groups that I can do. What you need to do is go into the suggested practice problems for chapter 2. You need to look at the questions that deal with functional groups and try them, okay? You need to practice identifying functional groups. So what we're going to do now is we're going to take a short break. I'll give you some time to study the functional groups, and then when we come back after the break, before we get into section 2.4, we're going to look at a couple of compounds and see if we can identify some functional groups.